Hello, and today we're going to talk about inelastic collisions. And so if you remember from the video on sort of setting up the definitions of these things, inelastic collisions only conserve momentum, not mechanical energy, okay? And yeah, of course, conservation of energy as a global principle still applies, right? The energy that is lost from the objects involved in the collision has to go somewhere, and I list a few examples there in the text. But it doesn't stay with the objects, and so we cannot rely on the kinetic energy of the system before the collision equaling the kinetic energy of the system after the collision, right? So for inelastic collisions, are the tool that we have available to describe what happens before and after a collision is limited to conservation of momentum. Okay? And conservation of momentum states that the total initial momentum of the system is going to be equal to the total final momentum of the system for the instant just before the collision happens to the instant just after the collision concludes, and they bounce off of each other or stick together or whatever it happens to be. So this is our tool, and a reminder, okay, that inelastic collisions can encompass a really wide variety of behaviors, but for all of them, this will apply. And I've written out what the expansion of these two terms would look like here. Okay, so it's just one term per object involved. And so you've got two objects here, and this is before, and this is after, as I've laid out here, okay, in color code. Okay, and a lot of inelastic collisions look a little bit like elastic collisions, right? You might have your two objects and they're coming towards one another, and then at some later time they've collided and they're bouncing off of one another, and they change their velocities, etc., etc. This could be, at least in cartoon form, an elastic so I have to be careful with my enunciation. It could be an elastic collision or an inelastic collision. And finding out which type it is sometimes given to us, and sometimes we can ferret it out by either comparing the energy before to the energy after, or by using relationship regarding the relative velocities of those two objects that we'll get into when we talk about elastic collisions. Okay, but for inelastic collisions, conservation of momentum only. Now, there are a couple of different ways we can go about solving these problems, okay? And they pop up all over our world and in physics. And let's take a look at a special type of inelastic collision called a perfectly inelastic collision. Okay. When we use the word perfectly here, what that means is that after the collision, as a result of the collision, I should say, the two objects that are colliding stick together and move with a single common velocity. And so our momentum equation reduces to, well, it's the same first line, okay? But reduces to, well, that's the same because they're still separate at this point, but reduces to this on the right-hand side of the equation, okay? Which reduces the number of unknowns in this equation by 1, and that's often a useful thing. Definitely simplifies the calculus, usually. Now, there's all kinds of examples of perfectly inelastic collisions. You could have one, for instance, where you have in this case, a rugby player wrapping up on another one when doing a tackle, and they, as they collide, become one object that moves with a common velocity as they then subsequently fall to the ground or something like that. Another kind of perfectly inelastic collision is one exemplified by what's called a ballistic pendulum. So if you have a pendulum, so you have a fixed point here and maybe a string or cable or something, and from the end of that, maybe a heavy block of wood. and you fire a projectile into it. So the before picture looks like this, with this thing coming in with quite a large amount of initial velocity, and this thing hanging stationary like that. Okay. And then at some later time, let me get a different color here, these two things collide and stick together so that the bullet is, or whatever projectile is embedded within this thing, and they move with some common velocity. Let's call it v final or something like that. Okay. Now in this case, the swing upwards with the two objects stuck together is an important part. Maybe we can come back and do an example problem with that sometime. But the basic idea in terms of just handling the collision between the bullet and the hanging pendulum is that the the conservation of momentum equation looks very much like this, but for this particular situation would look like, let's see, so the final momentum I've put in red. So both of the objects are moving together, so say mass of bullet plus capital M for the mass of this big wooden block times V final. And then initially, you have a momentum that's entirely contained within the bullet, right? The pendulum part is stationary before. And so you'd have mass of bullet times initial velocity, okay? And so the conservation of momentum equation, which starts out in a fairly general form, okay, lots of different terms, is reduced to a relatively simple form once you apply it to this specific situation. All right, so we might see that one again in a future presentation in some format. Okay. So those are inelastic collisions. What I'd like to talk about next is elastic collisions, and we'll get to that in the next video.